Yeah, hi. Good evening, everybody. I hope all you're able to see me. So the title today is Business Aligned Approach to Prioritizing Servicing Technical Debt. Um, so the keywords that are being used here, of course, technical debt, business aligned, and cloud applications. So there is a reason why I have chosen business alignment and cloud for various reasons. One is that we all understand technical debt is arises because uh, development community places priority on functional agility. They want to get that product out to the market quickly, but there is an underlying debt in the code, in the sense, the code is not elegant, it's not maintainable, there are performance issues, but it works. Now when it comes to cloud applications, what is the impact? Now if you take a typical cloud application, uh, many organizations are adopting cloud, but only 30% of the organizations, in our survey we found approximately 30% of the organizations adopting cloud, they say only they have seen business benefits. Now those reasons why the business outcomes are not as expected is could be various reasons, but one of the main reason is cloud is a distributed system, and there are three main risks arising out of distributed system, because distributed systems are very unpredictable in their runtime behavior. We will talk more about those and how it is connected with technical debt. So there are three risks arising out of cloud adoption for organizations, either when they migrate to cloud or whether they are um, developing cloud native applications. So one is the cloud applications ecosystem is failing to unlock value from cloud, which means the on-prem version and the cloud version are no different and there is no value. Second is cloud application ecosystem tends to fail more often than the on-prem version because of distributed failures. And third, very important, is the cost of cloud resources not commensurate with the business gains. You have cloud cost, but those costs are high and there is no corresponding business gains. Now, if you look at the pyramid here, the business success obviously depends on functional quality and technical quality. I use the word technical quality. I avoid the term non-functional quality or non-functional requirements, because technical quality seems to describe the importance much better than non-functional. So why I have taken technical quality is the on-prem version of any application and the cloud version. What differentiates the functional? There is a functional equivalence, but what differentiates the cloud version is high degree of expectation, is that it is highly performant, high throughput, highly resilient, highly secure and usable, and it's cost efficient. Now the technical quality in turn depends on the system design and architecture choices. When we talk about design and architecture, it's all about choice, not just diagrams, but it's all about choice. And then, of course, the underlying infrastructure. So this diagram indicates that the business success, there are risks to business success, and the business success um, is dependent on how well the technical qualities align to the business outcomes. For example, if the cloud system is a high speed trading platform, then you need the system to be high throughput, low latency, and high number of concurrent users. And there are multiple, and there could be the same technical metric could vary depending on the context. So the business outcome is dependent on technical quality, which in turn is dependent on the system design and architecture choices, especially in a distributed system like cloud. I move to the next slide. Now, the cloud architects and developers have to take decisions under great deal of uncertainty in a distributed system. Now, why this is so, and what is the implication? In a distributed system, everything is a trade-off. You trade off throughput with latency, you trade off performance with usability. If you want highly, I'm sorry, you trade security with usability, and everything is dependent on cost. You have to constantly, continuously trade off these technical quality goals, and then which in turn you have to optimize your design decisions in order to meet those technical quality goals. Now, all this has to be done under great deal of uncertainty, because cloud distributed systems, you have hundreds of components coming together, and it is not easy to determine how they will behave at runtime. Cloud is a world of VUCA, variability, uncertainty, complexity, and ambiguity. Variability because there is constant change in technologies, regulations, market user requirements. The cloud constantly undergoes change because the hyperscalers continue to provide more services. There is uncertainty, the usage patterns, design constraints, and the behavior is indeterministic. And there is a high degree of complexity in a distributed system. And then the requirements are often very ambiguous because the cloud has large geographical reach, and what is value and special requirement in one geography could be very different from the special requirements in other. So the summary here is that the business success depends on technical quality, which is all the performance, all the which is dependent on architecture decision. The technical quality is performance, throughput, latency, resiliency, reliability, availability. So that is going to be important. Now I will come to how this is related to technical debt. Now, technical debt is in the realm of often the realm of static analysis, whereas the actual product quality is at the runtime. Now, we need a way to connect these two and prioritize among the tens or hundreds of technical debt items we have in a typical distributed system. How do we prioritize? Because obviously we cannot do everything. Now, a quick look at why in a cloud this is important is the very characteristics of cloud which provide value, reliability, and cost efficiency. The same characteristics give rise to risks, value risk, failure risk, and cost risk if the design choices are not optimized. Now, I will again, as I said, I'll promise I'll connect that to technical debt in a minute. First is, a distributed system is highly scalable and redundant, but the same characteristics give rise to distributed failures if you have not architected and designed for resiliency. Cloud systems have high degree of abstraction and automation to help developers and operating personnel, helps you in agility, but the abstraction and automation often give rise to lack of visibility. Shared responsibility, we all know, cloud engineers here understand shared responsibility. There are certain things that the cloud hyperscalers are responsible for in security and reliability, and there are certain things that the developer is responsible for. So we have security on the cloud and security in the cloud. But then often, even though the responsibility documentation is very clear, there is lack of clarity because developers have to understand and remember, and there is so much cognitive load on developers. Often there is a mistake, and that technical debt gets added on because of that, which is not detected. Cloud is on demand and elastic, but that also could, an application could demand resources at runtime, so that the user demands could be met elastic way, but that could give rise to cost escalations. And then the next one is service explosion. There are so many services in a typical hyperscaler, Google Cloud or Amazon Cloud or Azure, but as the service explosion happens, more and more services come into play, the interfaces and interdependencies have become more and more complex. Of course, empowerment through self-service, but the self-service could also lead to non-configuration. Now, All this gives rise to risk to success if the trade offs and optimizations aren't done in a proper manner. Now, what are those decisions? The decisions could be three different dimensions. One is the choice of services, whether you are using a particular kind of ELB or serverless or server with server, messaging streams, compute, what kind of resources you want to use for compute. Then there is service configuration. Even that should come under technical debt because that also has an impact on runtime, uh, reliability or performance or efficiency. The third is design patterns. We all understand that design patterns, whether retry patterns, circuit breaker patterns, bulkhead patterns, there are so many patterns, and the right choice of patterns and the parameters set for those patterns. For example, retries, number of retries, retry timeouts, all that has a big impact on runtime technical quality. And every choice has a consequence, and that is going to be important for us in the next subsequent slides. So now what happens is the architecture degradations or technical debt. Here I'm talking more and more about architecture technical debt, and of course to some extent code debt. There are other debts, but here we specifically talk about technical debt in terms of architecture. Now, we've seen everybody tries to follow agile, and agile is supposed to increase feature velocity. But it's like adding more and more floors to a building that could actually cause architectural degradation because the architecture assumptions that you have made 5 years ago or 1 year ago will no longer be true when you add more and more features. For example, we had a trading platform, and as they added more and more commodities to the trading platform, the developers thought the underlying architecture doesn't have to be revisited. But when they added certain commodities to the trading platform, the pathways, the trace pathway were different that caused serious performance and security issues. So this is also a technical debt. Second is inherently developers will not have an easy way of assessing the impact of their choices at runtime because of complexity. So that leads to unpredictable outcomes, and that causes technical degradation, that causes system failures. Now, coming to a topic of discussion, how do we connect technical debt and quality? Now, what the challenge for developers, designers, and architects is that technical debt is a static analysis, whereas the quality and technical quality is a runtime. Now, we need a way to connect these two. Why do we need it? Because if you're running a code quality tool or you're running an architecture, software composition, or structure analysis tool in a static during the development, you get a bunch of findings, 25, 30, or 100. Now, developers tend to ignore because you cannot look at all of them and service all of them. It's like saying, now you go open a magazine or any website, you have a bunch of things that you should have, take salads, run in the morning, meditate, be mindful. There are so many things that, it's like a static, technical debt. Suppose I don't get up in the morning and exercise, like a technical debt. But what all will I do in a 24 hours? And what all can I eat in the 24 hours that I have? I cannot have every good stuff, healthy stuff. So now, what is important insofar as business impact is concerned? Now, if you tell me, Mahesh, you have to compete in the marathon, then I know what technical debt or what health debt I have to service. Now, I will do only that much that is required for me to compete or run in the marathon. Or if I have to be a swimmer, I will do that much that is required. Similarly, in a distributed system or a cloud which has huge impact on business outcomes, we need to be able to connect three things: the risk to success or the business outcomes, the runtime technical quality or technical debt, and the static technical debt. Today, there is no easy way of determining how all these connected. So, with the result that when a developer sees a bunch of technical debt items, developer tends to ignore those things because there is so much to be done. What do we do, right? I hope this is clear. So coming back, just as recap, as we go to the next step is business success, technical quality, system design and architecture, system design and architecture, suboptimal decisions lead to architectural technical debt, resulting in poor quality and resulting in suboptimal business performance. Now, how do we solve this problem? Now, one way to solve this problem is to adopt an empirical approach, um, what we call the experimental approach. Now, first and foremost is I don't know whether hyperlink works, so I'll have to move to the another slide. So what happens is first and foremost is we need to um, cascade the business success goals, define the business success goals into service flow performance goals. Now, unfortunately, I'm not able to use any hyperlink, so I'll have to move forward and bear with me until I go to that particular slide. This is the one, right? Now, how do we do goal drill down alignment? Now, it is important for us to translate business outcome goals to architecture quality goals or trace performance goals. For example, you have business outcome goals, revenue goals, customer goals, internal productivity improvement goals. Those goals have to be cascaded or translated into service flow performance goals. For example, payment flows goals, or if you're in insurance, underwriting service flow, underwriting value chain goals. And those goals, in turn, will have to be cascaded or decomposed into architecture trace performance goals. And these trace performance goals decide the trade offs and optimization and constraints. Now, we will use this concept and connect it with technical debt so that technical debt becomes aligned to business goals. So now we have seen this business success goals are translated into service flow performance goals from a business perspective and all the way down to the architecture trace performance goals. Now, what do we do with this? Now, from this, we derive the system architectural decisions, and we also look at static technical debt analysis using the tools. We have tools that provide code analysis. We look at the code analysis outcomes, outputs, performance issues, resiliency issues, security issues, or efficiency issues. And then we document this. And the next step is to do what we call the failure modeling. Now, failure and degradation modeling is a whiteboarding approach wherein we look at the current architecture or the design and some amount of high level code and see, given the business flows, given the critical business flows, how will this system tend to fail? How will this system tend to degrade? For example, if you're designing a core banking system, um, you have decided on a particular architecture, and then um, you look at in what ways the system is likely to um, have multiple credits and debits because lack of idempotency. So idempotency is a property by which, if in a distributed system, if there are multiple requests for the same transaction, the system should not reprocess it. For example, you have a credit, you want a user account to be credited with 100 euros, but then you see that it is taking a long time and the requester resends the request. Now, the risk here is if that second request and the first request was actually honored but not acknowledged, or the acknowledge got lost in the distributed system flow, the second request also goes, and that also credits the user with 100 euros. That's a problem. And all this is related to design choices, design decision which are not optimal, and certain amount of code and technical debt. Because when we designed and released the first version, we were not bothered so much about the technical quality, but more worried about minimal viable product and functionality. Now, after this, what do we do? We design experiments. We design experiments to prove or disprove the hypothesis. And those experiments are typically conducted in a offline, in a dev environment. And the in stimulus for the design experiment is taken from the production. From production, we derive the logs, we take the logs, and we mine how the system is being used. We also look at incidents, we look at failure events in the log and trace. All this goes into providing the stimulus for the offline uh, experiments in the dev environment. Now, what happens is once we execute the these experiments, once we execute these experiments, we use observability tools. I think many of us you would have heard about monitoring and observability. We use the observability tools to look at how the runtime technical quality is actually realized, and then connect that with the design choices made, and connect that with the debt, the technical debt, whether it is code or whether it is architectural choices, or we have missed out certain things we have missed out certain design patterns. So we connect all of this. And then while after connecting, there are arrows. Those arrows are not visible, unfortunately, when I'm showing it on the screen here. And I think there is a setup for there's a slide for this is a slide for experiment setup. So here, how do we conduct this experiment is, this is the architecture which is with its own distributed components. So we provide input vectors for various user loads, user profiles, service flow rates, service flow types, and row vectors. Now, some of you might say this is after all a performance engineering or performance testing. Yes, but much more than that. We do it much more thoughtfully, much more scientifically. We provide what we call the perturbation vectors. We introduce latency. We introduce certain disturbance or perturbation, delays and configuration changes. We introduce row vectors. Then we look at internal response, how the trace, whether there are internal latency issues, internal cost issues, if whether any services are being used much more than initially planned. Then we also look at the system response data, and then go back and check whether how many of them are critical, how many of these issues are critical from a, unfortunately I have to keep moving, how many of these technical quality issues are actually critical to business success, and then prioritize those technical debt items that are causing these technical quality um, failures or degradation. Now, in this definition, incident is not just failure modes. Incidents also includes certain degradation that happen under certain conditions. Normally, your performance or throughput or response time or resiliency will be okay, but under certain conditions, they will deteriorate or degrade. It's important as part of the experimentation to determine and discover those degradation modes. Now, after this, so what do we do? Now, this debt prioritization is done, and then we go and remediate the code, we remediate the architecture, and then this cycle continues. There are arrows between these boxes. Those arrows are not visible. Sorry about it. So this is a continuous cycle. Now, why this is continuous, required to be continuous? Because you are adding more and more features, you're adding more and more functionality, as functionality adds up to the system, there is a high likely chance that technical debt also adds up. So now there is another thing that is required here is that um, there are dev teams, there are ops teams. It's important to have a quality team or a chaos engineer or experimentation team to continuously provide this feedback, feed forward and feedback to the dev and ops team, so that all dev and ops team have the same behavior model of the cloud applications, so that the dev team is able to understand the impact of the decisions. Often what happens is ops team says we have a problem, the dev team says, look, I am not able to reproduce or replicate the problem. The problem gets closed. This will avoid if we have a continuous experimentation. The result of the experimentation is published to the ops team, published to the dev team, and there's a connect made between static analysis and runtime performance. So the summary here is that for a cloud or a distributed application, the technical debt mounts up rapidly, and this technical debt is in the form of suboptimal design and architecture choices. And this suboptimal architecture or design choices, including suboptimal code, will tend to degrade the technical quality, which in turn will inhibit or prevent the enterprise to realize the business outcomes, the very reason why they have adopted cloud. So I hope I hope this is quite useful and practical. We have been using it in complex, large systems in order to connect uh, static quality or technical debt on the development side, and the actual runtime technical quality on the runtime side. So with this, I end my presentation. This is supposed to be for 45 minutes, but I thought if there is any provision for any questions, I'll be glad to take the questions, and I will be very glad to continue our dialogue offline after this presentation. Thank you very much. Over to you, organizer.